All right, so this problem reads, two piloted satellites approach one another at a relative speed of 0.25 meters per second, intending to dock. The first has a mass of 4 times 10 to the third kilograms, and the second has a mass of 7.5 times 10 to the third kilograms. If the two satellites collide elastically, meaning they bounce off of each other, rather than dock, what is their final relative velocity? So we're going to make one assumption that they collide perfectly elastically. And that's going to be important because we want to remember that when there's a collision, a perfectly elastic collision, two things are conserved. First, momentum of the system is conserved. So we know that our final momentum has to equal our initial momentum of the system. Second, kinetic energy of the system is also conserved. And we're going to use both these ideas in order to solve this problem. So both kinetic energy of the system and momentum of the system is conserved in a perfectly elastic collision. All right, so let's start with the momentum. Let's first imagine what is our initial condition and what is our final condition. And there's some clues into this problem. It's not as clear because it says the relative speed of the two satellites is 0.25 meters per second. That means they could both be moving. One could be moving relative to the other. We have to sort of make an assumption, a model, in order to solve this problem. So since we know the relative speed is 0.25 meters per second, that's to the right, it's positive. We're going to use it as positive. Let's say that the object, satellite 2, is stationary and satellite 1 is moving towards it at 0.25 meters per second. That would give a relative speed. So if we do the frame of reference as if we are on satellite 2. So our initial condition then is going to have satellite 1 moving at 0.25 meters per second. This is the V initial of satellite 1. And satellite 2 has going to be not moving. It's not going to be moving. So it's at 0 meters per second. That gives me that relative velocity of 0.25 meters per second squared. Now, when they collide, both satellites will be moving. And we can sort of make a prediction if satellite 1 is moving. Now, satellite 2 is a little bigger, so the chances is that satellite 1 will be moving to the left in the final condition and satellite 2 would be moving to the right. That would be the case with satellite 2 being a larger object. All right, so relative to satellite 2. So let's start with that, our momentum relationship. We have P initial is equal to P final. We know that P initial is going to be the initial momentum of both satellites. But since satellite 2 is not moving, it doesn't have any initial momentum. So we have mass 1 times the initial velocity of satellite 1. That's going to equal mass 1 times the final velocity of satellite 1 plus mass 2 times the final velocity of satellite 2. Okay, so mass 1 is 4 times 10 to the third kilograms. It's traveling at 0.25 meters per second. That's going to equal 4 times 10 to the 3 kilograms times V final 1 plus by 7.5 times 10 to the third kilograms times V final 2. So now I'm going to simplify this equation and we find that 1,000 is equal to 4 times 10 to the third V final 1 plus 7.5 times 10 to the third V final 2. I have two unknowns. Well, with two unknowns, the only way for me to solve an equation with two unknowns is to have another equation with those same unknowns. How do we get that? Well, we know that the kinetic energy is also conserved because this is an elastic collision, a perfectly elastic collision. So we have the same initial and final conditions. We have to keep that in mind. We're going to use our kinetic energy relationship. All right. Well, the kinetic energy means that's the kinetic energy initial of object 1 plus the kinetic energy initial of object 2. That has to equal the final kinetic energy of object 1 plus the final kinetic energy of object 2. But again, object 2, satellite 2 is not moving, so that doesn't have any kinetic energy. All right, so we have 1/2 m1 times the initial speed, in this case, of object 1. I don't know why I put a v there. Got a little ahead of myself. Is going to equal 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Now, my halves can go away, and I am left with a relationship that has m1 times v1 squared, so 4 e to the third times 0.25 quantity squared is equal to 4 e to the third times v1 final squared plus 7.5 e to the third times v2 final squared. All right, I'm running out a little bit of room on my video. So I have a relationship, an equation here. This is, I think I can fit it in here. We have 250. Perfect. 250 is now equal to 4 e to the third v1 final squared plus 7.5 e to the third v2 final squared. All right, just getting off screen there. I'm going to be a little bit careful as I kind of peek over at the recording. I'll move this up just a smidge so it doesn't get off our screen. All right, so this is v2 final squared. Okay, getting a little tight. Same two unknowns as is up here. So I now have two equations with two unknowns. This is a solvable problem by whatever method you prefer. I prefer substitution. So what I'm going to do is I'm going to solve this equation for V2. So I'm going to solve for V2, right? So when I solve for V2, I get, I'm going to move that up here. So I'm just going to rewrite the equation so that we have a full slate here. So 1,000 equals 4 times 10 to the third V final 1 plus 7.5 times 10 to the third V final 2. And I'm going to solve for V final 2. So I'm going to bring this to the other side. I have 1,000 minus 4 times 10 to the third V final 1 is equal to 7.5 times 10 to the third V final 2. Divide both sides by 7.5 times 10 to the third. Now don't make that kind of common math mistake where you only divide one of those. Both these numbers have to be divided, and we end up with 0.133 minus 0.533 V final 1 is equal to V final 2. So now I have a relationship for V final 2 in terms of V final 1. And I can put that into this equation, right? So I can plug that into my equation down here. When I do that, I end up, so I'm going to plug it into this equation, I end up with 250 is equal to 4 times 10 to the third V final 1 plus squared plus 7.5 times 10 to the third V final 2 squared, which is 0.133 minus 0.533 V final 1, and this whole thing gets squared, all right? That whole thing gets squared. Now I have a single equation with just one unknown, and I can solve it. And it's a little messy, but it's fun algebra. And when we do that, we find that V final 1 is equal to negative 0.076 meters per second. Now, when you solve that equation, you're going to have to do a quadratic. It's a square, v final 1 squared. And a quadratic always means that we have two solutions. One of those solutions isn't going to make any sense, but the other one does. This one's the one that makes sense. First, we predict that it's going to be going in the opposite direction. But we also, the other one doesn't make sense because it's this value, super close to 0.25 meters per second. And that doesn't make sense. So this is the only one that physically makes sense for our situation. Once we have v final 1, I can plug this into that equation, and I can get v final 2. And v final 2, we find is equal to 1.173 meters per second. So it goes to the right after this collision, as we might predict, based on our understanding of kind of collisions and our intuitions about collisions. And so what the question really asks, what's the relative velocity of these two? So v final 2 is going to the right at 0.173, and v final 1 is going in the opposite direction to the left at 0.076. We would add these two numbers together to give that relative velocity. So imagine yourself on satellite 2, and you're zipping along to the right at 0.173 meters per second, and satellite 1 is not only moving in the opposite direction that you're moving, but you got to consider that you're moving. And so you add those two numbers together, and we get a relative velocity of 0.249 meters per second. All right? It's writing the values, the numerical values, not the negative in there. So it's moving away from you at 0.76 while you're moving away from it at 0.173. All right, so like I said, a little bit of messy algebra, super fun. Messy algebra is always fun. But recognizing these two features, that's what's key. That both those apply in this situation. And when both those apply, we are going to utilize that information, do a little substitution, two equations, two unknowns, and it's a solvable problem. All right, good job.